megawatts on your mind from LIGHTHIEF. We build it, we run it, we know what works, real projects, real returns. The renewable energy podcast that doesn't waste your time. Let's go.
We're talking about biogas. Biogas is the Cinderella of renewable energy. It's not sexy like solar. It's not dramatic like offshore wind. It doesn't feature in glossy presentations with sweeping aerial shots of pristine installations gleaming in the sunshine. Instead, biogas involves digesting organic waste, agricultural residues, food scraps, sewage sludge, energy crops, in large tanks that occasionally emit rather agricultural odors. It's industrial biology meets waste management meets energy production. And yet, biogas is quietly doing something that solar and wind cannot, providing dispatchable renewable energy. While solar produces when the sun shines and wind when the wind blows, biogas plants can run continuously, 24 hours a day, 365 days a year, producing predictable, controllable power. In an energy system increasingly dominated by intermittent renewables, this dispatchability is becoming extraordinarily valuable. Europe has over 20,000 biogas installations, producing roughly 20 billion cubic meters of biogas annually. That's equivalent to roughly 12 to 15 gigawatts of electrical capacity, depending on how you calculate it. Germany alone has over 9,000 biogas plants. Italy has nearly 2,000. France, UK, Czech Republic, Poland all have substantial and growing biogas sectors. But biogas remains misunderstood and often underappreciated. Many people in renewable energy know little about how biogas actually works, what's involved in building and operating plants, what the economics look like, or what role biogas can play in future energy systems. Today, we're going to demystify biogas. We'll explain what it is and how anaerobic digestion works. We'll walk through the components of a biogas plant, digesters, gas storage, generators, upgrading systems. We'll discuss what O&M involves and how it differs from maintaining solar or wind installations. We'll look at the numbers, how many plants exist, what they cost, what returns look like. We'll address the risks because there are substantial risks that many developers underestimate. And we'll discuss the future because biogas has an important role in Europe's energy transition, though perhaps not the role many people assume. At LIGHTHIEF, working with our partners, we develop biogas projects for clients across Europe. Not as many as we do solar farms. Biogas is more complex, more location-specific, and requires different expertise. But we've learned what works, what doesn't, and what makes the difference between profitable biogas plants and problematic ones. This episode is for developers considering biogas, for investors evaluating biogas opportunities, for farmers or agricultural businesses exploring on-farm generation, and for anyone in renewable energy who wants to understand this important but often overlooked technology. Shall we begin? And perhaps check which way the wind is blowing before we do? Let's start with basics. What exactly is biogas and how do you make it? Biogas is a mixture of gases, primarily methane and carbon dioxide, produced by the breakdown of organic matter in the absence of oxygen. This process is called anaerobic digestion. It's what happens naturally in swamps, rice paddies, landfills, and the digestive systems of ruminant animals. Humans have simply industrialized the process, controlling conditions to maximize gas production and capturing the gas for useful purposes. The composition of biogas is typically 55 to 75% methane, 25 to 45% carbon dioxide, with traces of hydrogen sulfide, ammonia, and other compounds. The methane is what you want. It's combustible and has energy content. The carbon dioxide is inert but reduces the energy density. The hydrogen sulfide is corrosive and smells appalling, like rotten eggs, and must be removed before the gas can be used. The anaerobic digestion process involves multiple stages of bacterial activity. First, hydrolysis breaks down complex organic compounds, carbohydrates, proteins, fats, into simpler molecules. Then, acidogenesis converts these into volatile fatty acids, alcohols, and other compounds. Acetogenesis further breaks these down into acetate, hydrogen, and carbon dioxide. Finally, methanogenesis produces methane from these compounds. Each stage is performed by different bacterial communities, each with specific environmental requirements. Temperature matters enormously. Biogas digestion typically operates in one of two temperature ranges: mesophilic at 35 to 40 degrees Celsius, or thermophilic at 50 to 60 degrees. Mesophilic is more common because it's easier to maintain and more stable. Thermophilic is faster and kills more pathogens, but requires more energy input for heating and is less stable. If conditions slip, the bacterial community can crash. The feedstock, what you put into the digester, determines both the quantity and quality of biogas produced. Different organic materials have different biogas yields. Energy crops like maize, silage, or sugar beet produce high yields, perhaps 300 to 400 cubic meters of biogas per ton of fresh material. Manure produces less, maybe 25 to 70 cubic meters per ton, depending on type and freshness. Food waste is variable, anywhere from 100 to 300 cubic meters per ton, depending on composition. The composition of feedstock also matters for process stability. Too much of one type can create problems. Too much protein produces excessive ammonia, which inhibits methanogenesis. Too much fat can cause floating layers that block mixing. Too much fibrous material can be difficult to break down. Successful biogas plants typically use mixtures of feedstocks, carefully balanced to optimize gas production while maintaining process stability. Retention time, how long feedstock remains in the digester, ranges from 20 to 80 days depending on feedstock type and process design. Energy crops and food waste digest relatively quickly. Manure and agricultural residues take longer. The digester must be sized to provide adequate retention time for the feedstock mix. A typical agricultural biogas plant might look something like this. Feedstock arrives and is stored in bunkers or silos. It's then fed into the digester, a large sealed tank, often concrete or steel, frequently insulated and sometimes partially buried. Inside, the digester is heated to the target temperature and continuously or periodically mixed to ensure contact between bacteria and feedstock. The biogas produced collects in the upper part of the digester or in a separate gas storage dome. The biogas is extracted, cleaned, at minimum removing moisture and hydrogen sulfide, and then used. Most commonly, it feeds into a combined heat and power unit, a CHP engine or gas turbine, producing both electricity and heat. The electricity is exported to the grid. The heat is used for process heating, warming the digester and incoming feedstock, and sometimes for additional purposes like heating buildings or drying crops. The digestate, the material remaining after digestion, is extracted from the digester and stored. This digestate is actually valuable. It's a high-quality organic fertilizer rich in nutrients and significantly more stable than raw manure. Many biogas plants derive substantial revenue or cost savings from selling or using digestate as fertilizer, reducing or eliminating the need for synthetic fertilizers. This is the basic concept. In practice, biogas plants can be considerably more complex, with multiple digester stages, sophisticated feedstock preparation, gas upgrading to biomethane quality, or integration with other processes. But the fundamentals remain the same. Anaerobic bacteria digest organic matter, producing biogas which is captured and used for energy production. Let's walk through the major components of a biogas plant, because understanding what's actually involved is essential for appreciating both the complexity and the O and M requirements, starting with feedstock reception and storage. Agricultural biogas plants need facilities to receive and store various feedstocks. Solid feedstocks like maize silage are typically stored in bunker silos, concrete structures similar to those used for animal feed storage. Liquid feedstocks like slurry or liquid manure are stored in tanks. Deliveries might arrive continuously or in batches, so adequate storage capacity is essential. Feedstock preparation is next. Some materials can be fed directly into the digester. Others require pre-processing. Maize silage might need chopping to reduce particle size. Food waste might need screening to remove packaging, plastics, or other contaminants. The goal is to produce a relatively homogeneous feedstock that can be reliably fed into the digester. The feeding system moves feedstock from storage into the digester. For liquid feedstocks, this typically involves pumps, often screw pumps or progressive cavity pumps capable of handling viscous, particle-laden material. For solid feedstocks, various systems exist: screw conveyors, belt conveyors, specialized solid-state feeders. The feeding system must be reliable because if feeding stops, gas production drops rapidly. The digester itself is the heart of the plant. As mentioned, this is typically a large sealed tank. Size varies enormously depending on plant capacity, from a few hundred cubic meters for small farm-scale plants to several thousand cubic meters for large industrial installations. The digester is heated, typically using hot water circulation through pipes or heat exchangers. Temperature must be maintained constantly. Max wire. Bacterial communities are temperature sensitive and fluctuations disrupt the process. Mixing is essential in most digesters. Without mixing, the feedstock stratifies. Lighter materials float, heavier materials settle, and the active bacterial population becomes concentrated in layers rather than distributed throughout. Poor mixing reduces gas production and can lead to process instability. Mixing can be mechanical, using large slow-speed agitators, or hydraulic, recirculating digester contents with pumps. Some plants use gas injection mixing, where biogas is compressed and injected through nozzles at the bottom of the digester, creating circulation. Gas storage is necessary because gas production is relatively constant, while gas consumption for electricity generation might vary. Small plants often have integrated gas storage, a flexible dome on top of the digester that expands and contracts. Larger plants typically have separate gas storage, often a double membrane gas holder where biogas is stored between two layers of membrane at slight overpressure. Gas treatment removes unwanted components. At minimum, moisture must be removed. Biogas is saturated with water vapor, which condenses in pipelines and equipment, causing corrosion and blockages. This is typically done with condensation, cooling the gas so water condenses and drains away, or with desiccants. Hydrogen sulfide must also be removed. It's corrosive to engines and equipment. Common methods include biological desulfurization in the digester itself, chemical scrubbing, or activated carbon filtration. The combined heat and power unit converts biogas into electricity and heat. This is typically a gas engine, similar to a natural gas engine, but modified for biogas's lower energy content and presence of contaminants. Engine sizes range from tens of kilowatts for small plants to several megawatts for large installations. The engine drives a generator producing electricity. Waste heat from the engine, from cooling water and exhaust, is recovered using heat exchangers and used for process heating and other purposes. Some plants, instead of CHP, upgrade biogas to biomethane, essentially purified to natural gas quality. This involves removing not just hydrogen sulfide and moisture, but also carbon dioxide, increasing methane concentration to over 95%. Upgrading technologies include pressure swing adsorption, membrane separation, or chemical scrubbing. The biomethane can then be injected into the natural gas grid, used as vehicle fuel or sold as renewable gas. Digestate storage and handling is the final major component. The digestate extracted from the digester must be stored until it can be applied to land as fertilizer or sold. Storage requirements vary by country. Germany requires 6 months of covered storage capacity. The storage must prevent ammonia emissions and manage runoff. Many plants separate digestate into solid and liquid fractions using screw presses or centrifuges. The solid fraction is easier to transport and handle, while the liquid fraction can be applied directly as liquid fertilizer. Additional infrastructure includes electrical equipment, transformers, switchgear, grid connection, similar to any power generation facility. Control systems monitor and manage all aspects of the process: temperatures, feeding rates, gas production, engine operation. Emergency systems like flares to safely burn biogas if it cannot be used, and safety equipment for confined space entry and gas detection. The overall complexity is substantial. A biogas plant is part agricultural facility, part chemical plant, part power station. It requires expertise in biology, chemistry, mechanical engineering, and electrical systems. This complexity is part of why biogas remains relatively niche compared to solar or wind. It's significantly more complicated to build and operate. Right, let's discuss what's actually involved in operating and maintaining a biogas plant. This is where biogas diverges dramatically from solar or wind O&M. We're not just maintaining electrical and mechanical equipment. We're managing a biological process. Daily operations start with process monitoring. Operators check key parameters multiple times per day: digester temperature, pH, gas production rate, gas quality, feeding rates. Modern plants have automated monitoring with alarms, but human oversight remains essential. Experienced operators can detect problems from subtle changes in parameters before automated systems trigger alarms. Feeding management is a daily activity. Calculating and preparing the feedstock mixture, operating feeding equipment, ensuring consistent feeding schedules. This sounds routine but requires judgment. If feedstock quality varies, maybe the maize silage from this field is wetter than usual, feeding rates might need adjustment. Too much feeding overloads the digester, too little feeding reduces gas production. The CHP engine requires daily attention. Checking oil levels, coolant, operating parameters, alarms. Engines running on biogas require more maintenance than those on natural gas because biogas contains more contaminants even after cleaning. Spark plugs, oil, and filters need more frequent replacement. Weekly activities include more detailed process monitoring, laboratory analysis of feedstock and digestate, measuring parameters like volatile solids content, chemical oxygen demand, nutrient concentrations. These analyses inform feeding strategies and help maintain process stability. Mixing equipment needs regular inspection. Agitators have seals, bearings, and motors that wear. Pumps handling thick, fibrous material require maintenance. Blockages in pipework must be cleared. This is often physically demanding work. You're dealing with thick, viscous, sometimes challenging material. Gas cleaning equipment requires regular maintenance. Activated carbon filters need replacement when saturated. Biological desulfurization systems need monitoring to ensure sulfur-eating bacteria remain active. Gas compressors and blowers require standard mechanical maintenance. Monthly activities include engine service, oil changes, filter replacements, visual inspections, performance testing. Biogas engines typically require major service every 2,000 to 5,000 operating hours depending on manufacturer specifications. This is considerably more frequent than diesel or natural gas engines. Heating system maintenance is essential. Pumps, heat exchangers, control valves all require periodic inspection and service. Any heating system problem directly affects digester temperature and therefore gas production. Quarterly activities include comprehensive process audits, detailed analysis of feeding data, gas production, digestate quality, energy yields. Identifying optimization opportunities. Could different feedstock ratios improve performance? Is retention time optimal? Are there inefficiencies in energy use? Structural inspections of digesters, storage tanks, and buildings. Looking for corrosion. Hydrogen sulfide creates corrosive conditions. Checking seals and membranes for damage. Verifying gas tightness. Annual activities include major equipment service. CHP engines might require major overhauls. Cylinder head work, valve replacement, turbocharger service. This often requires specialized contractors and can cost tens of thousands of euros. Complete system testing, safety systems, emergency shutdown, flare systems, gas detection. Regulatory inspections. Most countries require annual safety inspections of pressure vessels, explosive atmosphere equipment, and other regulated components. Now, the biological aspects that make biogas O&M unique. The digester contains a complex ecosystem of bacterial communities. These communities are sensitive to various stresses. Temperature fluctuations, pH changes, toxic compounds, overfeeding, underfeeding, all can disrupt the bacterial balance. When the process becomes unstable, recovery can be slow. You can't just turn it off and restart like a solar inverter. If bacterial communities crash, you might need to restart the digester, which means inoculating with digestate from a healthy digester and gradually building up the bacterial population over weeks. Common process problems include acidification, when acid-producing bacteria outpace methane-producing bacteria, causing pH to drop and gas production to cease. This is often caused by overfeeding or too much easily digestible material. Recovery requires stopping or reducing feeding and possibly adding alkali to raise pH. Foaming is another common issue. Excessive foam forms on the digester surface, reducing effective volume and sometimes blocking gas extraction. Causes include certain feedstock types, protein-rich materials, or process instability. Solutions include mechanical foam breaking, chemical anti-foam agents, or adjusting feedstock. Hydrogen sulfide levels can increase, causing equipment damage and safety concerns. This happens when sulfur-containing compounds in feedstock are converted to hydrogen sulfide. Management involves better feedstock selection, dosing with iron salts to precipitate sulfur, or improving biological desulfurization. Substrate scum formation, floating layers of fibrous material that don't digest, can occur with certain feedstocks. This reduces effective digester volume and can block mixing. Prevention involves better feedstock preparation and more aggressive mixing. The practical challenge with biogas O&M is that it requires both engineering skills and biological process understanding. Many O&M teams come from one background or the other, but not both. Engineers understand the equipment but not the biology. Biologists understand the process but not the mechanical systems. The best biogas operators have or develop both skill sets. We've taken over O&M contracts for biogas plants that were underperforming significantly. Often the problem wasn't equipment failure, but process mismanagement. Poor feeding strategies, inadequate monitoring, failure to recognize and respond to process instability. Improving performance required understanding both the biology and the engineering. Training is more complex for biogas than for solar. A solar technician needs electrical and mechanical training. A biogas operator needs that plus process chemistry, microbiology, agricultural knowledge, and often hazardous material handling certification for digestate and feedstock management. Safety is another consideration. Biogas plants have confined spaces, digesters, tanks, storage areas, requiring specific safety protocols. Biogas itself is flammable and can form explosive atmospheres. Hydrogen sulfide is toxic at relatively low concentrations. Digestate can contain pathogens. Personal protective equipment and safety procedures are essential. The O&M cost for biogas is significantly higher per kilowatt than for solar or wind. A typical figure might be 40 to 80 euros per kilowatt installed capacity annually, compared to 15 to 30 euros for solar. This reflects the greater complexity, more intensive labor requirements, and higher maintenance costs for engines and mechanical equipment. Let's look at the actual numbers for biogas in Europe. How many plants exist? How much energy do they produce? What are the economics? Is this actually a good business? Starting with installed capacity, Europe has approximately 20 to 22,000 biogas plants producing around 20 billion cubic meters of biogas annually. This sounds impressive until you convert it to electrical capacity. It's equivalent to roughly 12 to 15 gigawatts, depending on how efficiently the biogas is used. For comparison, Europe has over 200 gigawatts of solar and over 200 gigawatts of wind. Biogas is roughly 5 to 7% of renewable electricity capacity. Germany dominates European biogas with over 9,000 plants. This is more than the rest of Europe combined. German dominance reflects very generous feed-in tariffs implemented in the 2000s and 2010s, making biogas extremely profitable. At the peak, German farmers were building biogas plants primarily to receive subsidies rather than for genuine waste management or energy needs. Italy is second with approximately 1,800 to 2,000 plants. Italian support schemes were also generous, though less so than Germany. France has around 1,200 plants. UK has around 700. Czech Republic around 600. Poland is developing but still has only 200 to 300 plants. The support schemes haven't been as attractive. The technology mix varies by country. Germany's plants are predominantly agricultural, farm-based installations using energy crops and manure. Italy has more industrial biogas using food waste and agricultural residues. UK has more anaerobic digestion treating sewage sludge and food waste. This reflects different support schemes incentivizing different feedstocks and applications. Biomethane production, upgrading biogas to natural gas quality, is the fastest growing segment. Europe produces roughly 3 to 4 billion cubic meters of biomethane annually, mostly in Germany, France, and Italy. This is still only about 1% of European natural gas consumption, but growth is rapid. Several countries have specific targets for biomethane production. Investment costs for biogas plants vary widely depending on size, technology, and location. A rough figure for agricultural biogas with CHP is around 4,000 to 7,000 euros per kilowatt of electrical capacity. So a 500 kilowatt plant might cost 2 to 3.5 million euros to build. Biomethane plants are more expensive, typically 6,000 to 10,000 euros per normal cubic meter per hour of biomethane production capacity. The upgrading equipment adds significant cost. Operating costs, as mentioned, are substantial. Total operating costs, including feedstock, labor, maintenance, and other expenses, might be 200 to 400 euros per kilowatt installed capacity per year. For a 500 kilowatt plant, that's 100 to 200,000 euros annually. Revenue depends entirely on support schemes in local markets. In Germany, under the Renewable Energy Act, biogas plants receive guaranteed tariffs ranging from roughly 150 to 250 euros per megawatt hour, depending on size and commissioning date. With a capacity factor of around 70 to 85%, biogas runs much more continuously than solar or wind. A 500 kilowatt plant might generate revenue of 500,000 to 700,000 euros annually from electricity. Heat sales provide additional revenue if there's a local market. District heating, industrial processes, greenhouse heating. Heat prices vary but might be 30 to 50 euros per megawatt hour thermal. If you can sell all the waste heat from the CHP, this adds substantial revenue. Digestate sales or savings from reduced fertilizer purchases add further value. Precise figures vary, but digestate from a 500 kilowatt plant might be worth 20 to 50,000 euros annually in fertilizer value. So total revenue might be 550 to 800,000 euros annually. Subtract operating costs of 100 to 200,000 and debt service, assuming 50 to 60% debt financing, and you're potentially looking at earnings before tax of 100 to 300,000 euros annually. Return on equity might be 8 to 15%, depending on specific circumstances. These numbers explain why thousands of biogas plants were built in Germany and Italy. The economics were genuinely attractive. But they also reveal the problem. Without subsidies or high energy prices, biogas economics become marginal. The capital costs are high, operating costs are substantial, and unsubsidized electricity prices often don't provide adequate returns. In countries without strong support schemes, biogas development has been limited. The plants that do exist often have specific circumstances making them economically viable. Waste treatment operations where tipping fees provide revenue, or industrial facilities with waste streams and on-site heat demand. The risk profile for biogas investments is higher than for solar or wind. Technology risk exists. Biological processes are more uncertain than photovoltaic generation. Operating risk is substantial. Plants require skilled operators and can underperform if poorly managed. Feedstock risk exists. Securing long-term feedstock supplies at predictable costs can be challenging. Regulatory risk is significant. Support schemes change, sometimes retroactively, and digestate regulations can tighten. But biogas also has revenue diversification that solar lacks: electricity, heat, digestate, potentially carbon credits. And in specific circumstances, farms with abundant manure, food processors with waste streams, wastewater treatment plants. Biogas can make excellent economic sense even with modest or no subsidies. Let's be direct about what can go wrong with biogas projects, because there are substantial risks that many developers underestimate until they are dealing with the consequences. First, process stability risk. Anaerobic digestion is a biological process depending on living organisms. These organisms can and do die if conditions become unsuitable. We've seen plants where process crashes resulted in months of downtime while the digester was emptied, cleaned, and restarted. During this time, there's no gas production, no revenue, but ongoing costs for debt service and basic maintenance. Process crashes can be caused by various factors. Toxic compounds in feedstock, maybe contaminated food waste or agricultural chemicals, overfeeding or sudden changes in feedstock composition, temperature control failures. Each cause requires different remediation, but all result in lost production and potentially substantial recovery costs. Second, feedstock availability and cost risk. Many biogas plants depend on specific feedstocks, perhaps maize silage from local farms or food waste from nearby processors. If feedstock availability changes or costs increase, plant economics deteriorate rapidly. We've seen situations where a biogas plant was designed assuming a certain price for maize silage, but then commodity prices increased, or local farmers decided to sell their maize for animal feed or ethanol production instead. leaving the plant short of feedstock or paying much higher prices. When feedstock costs increase by 20 or 30%, which can happen with agricultural commodity price swings, plant profitability evaporates. Energy crop-based biogas faces particular scrutiny because of the food versus fuel debate. Growing crops purely for energy production, using land and resources that could produce food, is increasingly controversial. Some countries restrict or prohibit the use of dedicated energy crops for biogas. If regulations change to ban or limit energy crops, plants depending on them face severe problems. Third, equipment reliability issues. CHP engines running on biogas are working hard. High operating hours, corrosive environment, fuel quality variations. Engine failures are common. Major overhauls are expensive, potentially 50 to 100,000 euros or more for a larger engine. If you have only one engine and it fails catastrophically, the plant stops producing until repair or replacement is completed, which might take weeks or months. Some plants install two smaller engines instead of one large engine, providing redundancy. But this adds capital cost. It's a trade-off between redundancy cost and production risk. Fourth, regulatory changes. Biogas depends heavily on support schemes. When governments decide to reduce or eliminate subsidies, as has happened in various countries, plant economics can become untenable. In some cases, subsidies have been reduced retroactively, affecting existing plants that were built based on different economic assumptions. Germany reduced feed-in tariff rates multiple times, and some plant operators found themselves with debt obligations based on initial tariff projections, but actual revenues significantly lower. Some plants became economically unviable. Digestate regulations can also change. Stricter requirements for digestate storage, application restrictions, or classification as waste rather than fertilizer can substantially increase costs. Denmark, for example, has very strict regulations on nutrient management, making digestate handling more complex and expensive. Fifth, community and environmental opposition. Biogas plants can generate complaints about odor, traffic from feedstock deliveries, visual impact, and occasionally noise from equipment. Local communities sometimes oppose new plants or expansion of existing ones. Odor is particularly problematic. Despite best practices, biogas plants occasionally smell. If poorly managed, perhaps with uncovered feedstock storage or inadequate digester sealing, odors can be substantial and generate serious community opposition. Environmental incidents also occur. Digestate spills into watercourses have happened in various countries. A large digestate spill can cause serious environmental damage. The high nutrient content causes eutrophication and oxygen depletion in water bodies, killing fish and other aquatic life. The legal and financial consequences are severe. Sixth, gas quality and utilization issues. If gas quality is poor, high hydrogen sulfide, moisture, or contaminants, it damages equipment. We've seen CHP engines with severely reduced lifetime because gas cleaning was inadequate. Engine rebuilds required far more frequently than expected, destroying project economics. For biomethane plants upgrading to grid quality, meeting gas quality specifications can be challenging. If the gas doesn't meet specification, you cannot inject it into the grid. This requires backup plans or storage capacity to buffer production. Seventh, operator skill dependence. More than solar or wind, biogas plant performance depends critically on operator skill. A skilled operator can maximize production, maintain process stability, and minimize downtime. A poor operator can cause process crashes, equipment damage, and chronic underperformance. Finding and retaining skilled biogas operators is challenging. The knowledge required is specialized. Training is complex. Turnover can be problematic, particularly in rural areas where the plants are often located. Some plants cycle through multiple operators, each time experiencing learning curve issues and potential process problems. Eighth, technology risk for newer concepts. While conventional anaerobic digestion is mature technology, various newer concepts carry additional risk. Dry fermentation processes, two-stage digestion systems, co-digestion with unusual feedstocks, all have potential advantages but also higher uncertainty. Some innovative biogas projects have failed to achieve design performance or required extensive troubleshooting and modification. Technology providers sometimes oversell capabilities, leaving plant operators with systems that don't work as promised. The practical lesson from all these risks: biogas is considerably more complex and risky than solar or wind. It requires more sophisticated development, better operational management, and realistic expectations about performance variability. It's not a set and forget technology. It requires ongoing active management. Right? Let's discuss where biogas is heading in Europe. What role will it play in future energy systems? Is it a growing sector or a sunset technology? The answer is nuanced. Biogas as we've known it, predominantly energy crop-based agricultural biogas in Germany, is likely declining or stagnant. The environmental concerns about dedicating agricultural land to energy production, the relatively modest climate benefits when life cycle emissions are properly accounted for, and reducing subsidies all point toward this model being less favored going forward. But biogas from genuine wastes, agricultural residues, manure, food waste, sewage sludge, has a strong future. European waste policy is increasingly pushing organic waste away from landfills and incineration toward biological treatment. Anaerobic digestion is one of the best options for treating these wastes while recovering energy. The European Green Deal and farm-to-fork strategy emphasize circular economy principles. Biogas fits perfectly, taking waste materials, extracting energy, and returning nutrients to agriculture as digestate. This circular approach is exactly what European policy encourages. Specific trends are shaping biogas's future. First, biomethane production is growing rapidly. Instead of burning biogas in CHP engines, upgrading to natural gas quality and injecting into gas grids provides more flexibility and often better economics. Biomethane can substitute for fossil natural gas in heating, industry, or transport. It's fungible. Once in the gas grid, it's indistinguishable from conventional gas. Germany aims for 10 billion cubic meters of biomethane annually by 2030, up from about 1 billion currently. France targets 6 billion cubic meters by 2030. Italy has similar ambitions. If achieved, these targets would represent substantial growth in biomethane production. Second, integration with agriculture is becoming more sophisticated. Precision farming, precision nutrient management, using digestate to reduce synthetic fertilizer dependence. Biogas is increasingly seen as part of sustainable agriculture rather than just energy production. Third, advanced feedstocks are being explored. Algae, seaweed, grass from landscaping and roadside maintenance, invasive plant species. None of these are commercially significant yet, but research continues. The goal is to use feedstocks that don't compete with food production and might provide additional environmental benefits. Fourth, biogas plants are being integrated with other renewable energy systems. Solar or wind electricity can power biogas upgrading equipment. Excess renewable electricity can produce hydrogen via electrolysis, which can be mixed with biogas or used separately. Biogas provides dispatchable generation that complements intermittent renewables. Fifth, carbon capture and storage or utilization with biogas is being explored. The carbon dioxide separated during biomethane upgrading could be captured rather than released to atmosphere. Since this CO2 was originally absorbed from the atmosphere by plants, capturing it creates negative emissions. A few pilot projects are exploring this concept. Sixth, small-scale biogas is developing. Containerized, standardized biogas systems for individual farms or small communities. These reduce capital costs through standardization and expand the addressable market to smaller feedstock sources that can't justify large custom installations. From a market perspective, the opportunity is shifting. New subsidized agricultural biogas development in Germany is largely finished. The generous tariffs that drove the boom are gone. But opportunities exist in other countries with developing support schemes, in biomethane where policy support is growing, and in waste-to-energy biogas serving environmental rather than purely energy policy goals. At LIGHTHIEF, working with our partners, we develop biogas projects for clients across Europe. Our focus is on waste-based feedstocks and plants that make economic sense beyond pure subsidy dependence. Industrial biogas treating food processing waste, agricultural biogas integrated with farming operations, providing value through waste management and digestate production, and increasingly, biomethane projects supplying renewable gas markets. The practical reality is that biogas will remain a relatively niche renewable energy technology. It's not going to achieve the scale of solar or wind, but it has important roles in waste management, sustainable agriculture, and providing dispatchable renewable energy. In future energy systems with high penetrations of intermittent renewables, the ability to generate renewable electricity or gas on demand becomes increasingly valuable. And for developers and investors, biogas offers opportunities but requires different expertise than solar or wind. You need understanding of biology and agricultural systems, not just engineering and finance. Projects are more bespoke and less standardized, but for those with appropriate capabilities, returns can be attractive. The O&M opportunity in biogas is substantial. The existing installed base of 20,000 plants across Europe needs ongoing operation and maintenance. Many plants have inadequate O&M, providing opportunity for professional providers. As plants age, O&M intensity increases, and as new biomethane plants are built with more complex upgrading technology, the O&M requirements and value increase. Europe's path to climate neutrality requires multiple solutions, not just solar and wind. Biogas provides renewable energy from waste streams, reduces agricultural emissions, supports circular economy objectives, and offers dispatchability. It's not the star of the renewable energy show, but it's a solid supporting actor that plays an important role in the overall production. So we've explored biogas, what it is, how it works, what's involved in building and operating plants, what the numbers look like, what risks exist, and where it's heading. Key takeaways. Biogas is fundamentally different from solar or wind. It's a biological process producing dispatchable renewable energy from organic waste. The technology is mature but complex, requiring understanding of both biology and engineering. O&M is more intensive and requires more specialized skills than solar or wind. The economics vary dramatically depending on support schemes, feedstock costs, and local market conditions. In countries with good support, biogas can be quite profitable. Without support, it requires specific circumstances, waste treatment needs, heat demand, digestate value, to make economic sense. Risks are substantial: process stability, feedstock availability, equipment reliability, regulatory changes. Biogas is not a low-risk investment. It requires careful development, skilled operation, and realistic expectations. The future is not mass deployment of new energy crop biogas. That model is declining. The future is waste-based biogas and biomethane serving circular economy and sustainable agriculture goals. Growth will be steady but not explosive. Europe has over 20,000 biogas plants producing roughly 5 to 7% of renewable electricity. This will grow modestly, perhaps doubling over the next 15 to 20 years. But biogas will remain a relatively small part of the renewable energy mix compared to solar and wind. For O&M providers, biogas represents interesting opportunity. The installed base needs professional maintenance. Many plants underperform due to inadequate O&M. The complexity and biological aspects create barriers to entry, limiting competition and protecting margins for capable providers. For developers and investors, biogas requires different evaluation criteria than solar. You're not primarily betting on technology or commodity equipment prices. You're betting on biological process management, feedstock logistics, local regulation, and operational expertise. Success requires capabilities beyond what's needed for solar or wind development. Biogas is the unglamorous workhorse of renewable energy. It doesn't feature prominently in climate conferences or glossy marketing materials. It occasionally smells like a farm, but it quietly performs important functions: managing organic waste, producing renewable energy on demand, returning nutrients to agriculture, supporting rural economies. In future episodes, we'll continue exploring different aspects of renewable energy development and operations across various technologies and markets. We'll share more practical lessons from actual project experience, discuss what works and what doesn't, and keep providing the kind of honest assessment that you won't find in promotional literature. This is LIGHTHIEF, reminding you that not all renewable energy technologies need to be glamorous to be valuable. Sometimes the most important work happens in unglamorous facilities, processing agricultural waste and producing steady, reliable, renewable energy. Until next time, may your digester stay stable, your feedstock stay available, and your process never crash at 3 in the morning.